Good morning, class. Welcome back to AET 830 Internet of Things Basis and Applications. In this unit, we will talk about the application of IoT in digital and smart manufacturing. In this unit, we will first give an introduction and recap IoT, and then we will talk about sensor networks and manufacturing services. We will also look into a variety of applications of IoT technologies in the manufacturing domain. A majority of the content in this class is from the paper listed here. If you're interested in this topic, you are more than welcome to read about more details in this paper. The manufacturing sector has a large footprint in the US economy, producing a gross output of 2.2 trillion in 2016, 11.7% of the total American GDP. To achieve competitive advantages in global market, modern manufacturing enterprises strive to create new products or services with exceptional features such as adaptation, customization, responsiveness, quality, and reliability at unprecedented. New products have become an integral and indispensable part of everyday life. For example, phones and automobiles are not just communication and travel devices. They are becoming embedded with services that may then act as personal devices. Products are becoming increasingly self-aware. As a result, manufacturing systems are becoming increasingly complex and therefore deploy advanced sensing technologies to increase information visibility and system controllability. Notably, Industry 4.0 is driving manufacturing enterprises to become a new generation of cyber-physical systems towards network-enabled smart manufacturing. The smartness level depends, to a great extent, on data-driven innovations that enable all information about the manufacturing process to be available wherever it is needed, and in an easily comprehensive form across the enterprise and among the connected enterprises. As smart manufacturing becomes a trend impacting business and economic growth, a large amount of network machines are used increasingly to carry out manufacturing operations. These machines may carry out the same of different functions or tasks, and some machines rely heavily on the output from other machines, for example, finite product line. The connection between network machines may also be configured dynamically to increase flexibility and adaptation to customized tasks. As a result, the smart synergy of network machines is critical to improving the performance of manufacturing systems. One critical enabling technology for smart manufacturing is the Internet of Things, which in the formation of a global information network composed of large numbers of interconnected things. Here, manufacturing things may include materials, sensors, actuators, controllers, robots, human operators, machines, equipment, products, and material handling equipment, to name just a few. The Internet-based IoT infrastructure provides an unprecedented opportunity to link manufacturing things, services, and applications to achieve effective digital integration of the entire manufacturing enterprise. This integration can be stemmed from enterprise resource planning to supply chain management to manufacturing execution system to process control systems. However, the rapid growth of large-scale IoT sensing leads to the creation and manifestation of big data that are stored locally or in data repositories distributed all over the world. Realizing the full potential of big data from smart manufacturing requires fundamentally new methodologies for large-scale IoT data management, information processing, and the manufacturing process control. For example, the IoT may deploy a multitude of sensors to continuously monitor machine conditions and then transmit data to the cloud. IoT data includes not only historical sensor signals and measurements collected from a large number of machines, but also online data from in-situ monitoring of machines. The data can be retrieved easily from the cloud platform to distributed computers for parallel processing and used to extract useful information and prototype algorithms for deployment in the cloud or in the IoT things. However, very little has been done to leverage sensing data, known as machine signatures, from large-scale IoT networks of machines to develop new methods and tools to manufacturing systems diagnostics, prognostics, and optimization. Smart manufacturing goes beyond the automation of manufacturing shop floors, but rather depends on data-driven innovations to realize high levels of autonomy and optimization of manufacturing enterprises. As IoT and big data lead to the realization of cyber-physical manufacturing systems, the physical world is reflected in the cyberspace through data-driven information processing, modeling, and simulation. Analytics in the cyberspace explore the knowledge and useful information acquired from data to fit optimal actions or control schemes back to the physical world. Cyber-physical integration and interaction are indispensable to realize smart manufacturing. Before we move into the topic into more details, let's briefly review the evolution of the Internet. The Internet's reach and connectivity have touched every aspect of human endeavor. It is estimated that around 47% of the world population were Internet users in 2015. Nowadays, the percentage is already more than 70%. Figure 1 shows the evolution from before the Internet to the IoT. So this is figure 1. We can see how Internet has evolved in the past, I would say, more than 100 years. So the detailed description can be found here in these slides. The concept of an IoT was first coined by Aston at the IoT Auto ID Center in 1999. The term IoT means the formation of an internet composed of large numbers of interconnected things. Here the things refers to a global network infrastructure that uses the TCP/IP protocol to connect and remotely control things. Things refer to any objects that have unique identities and can sense, collect, or exchange data about environmental and operational dynamics. Examples of things include vehicles, sensors, actuators, machines, controllers, robots, and human operators. In practice, the IP address or a universal unique identifier are commonly used to designate a thing. The key technologies that integrate things into IoT ecosystems include RFID, wireless sensor network, and mobile computing, which are discussed briefly in the following sections. RFID technology reads and queries RFID tags attached to an object to automatically identify, monitor, and track the objects using radio waves. The basic components of RFID technology are RFID tags, RFID readers, and backend signal processing and IT infrastructure. The RFID tag contains a small microchip that stores data and processes information, as well as an antenna that can retrieve and transmit data to the reader. RFID reader transmitted and encoded interrogating signal to all tags within range and read out their stored information. Unlike barcodes, the tag does not have to be within the range of sight, but only in the range of radio waves. Based on the type of tag and reader, RFID systems are commonly classified into 3 categories. That is, active reader, passive tag, active reader, active tag, and passive reader, active tag. RFID offers a variety of advantages such as low cost, battery-free operation, long range, and long lifetime. It is worth mentioning that RFID systems have been used prominently in manufacturing enterprise operations, especially for work in process tracking, inventory control, and supply chain visibility management. Wireless sensor network mainly use spatially distributed autonomous sensors to sense and monitor environmental and operational dynamics of a company's system. Rapid advances in wireless sensor network contribute significantly to the implementation of IoT because things are much easier to connect to each other when many machines are equipped with the wireless sensors. Each wireless sensor network sensor consists of several components. For example, they will have a radio transmitter, transceiver to transmit data and receive control signals. They have a microcontroller providing embedded computing, and they have an analog circuit for signal processing. They also have an embedded operating system and a power source. Large numbers of wireless sensor network sensors are commonly organized into three different types of network topologies: star cluster tree and multi-hop mesh. Because a microcontroller is embedded into sensor nodes to improve the local processing capability, each individual sensor becomes smarter in IoT. Therefore, decision-making can be enabled at different levels of an IoT system, that is, cloud processing, gateway computing, or embedded intelligence in sensor nodes. Wireless sensor networks have been used widely for stable social monitoring, landslide detection, traffic monitoring, and machine health monitoring. There are some challenges including the latency, bandwidth, and interference that prevent the ubiquitous application of wireless sensor network in industry. But things are getting better nowadays. Mobile computing is another technology for IoT. Smartphones and tablets bring significant changes in almost every walk of life, including the manufacturing industry. Now the smartphones are equipped with internet connectivity, advanced processors, and embedded sensors to attain acceleration, ambient light, altitude, barometric pressure, GPS location, proximity, and image. As a result, it's easier to integrate mobile computing with IoT systems. In the past few years, the interplay between IoT systems and mobile phones has significantly increased. The integration of mobile phones with IoT near users promise to improve sensing modalities, increase information processing capability, and also provide better decisions and services in real time. RFID, wireless sensor networks, and mobile computing contribute significantly to the development of IoT sensing systems. IoT sensor nodes are deployed to collect and send data to cloud data centers, while a user can control the IoT remotely through the internet. The stored data and analytical results are readily available to users anywhere and at any time using a web-based user interface. As there are different types of IoT sensors, optimal scheduling and planning algorithms for power and computing resources are needed urgently. The existence of heterogeneous sensing network also requires seamless information exchange and data communication through different protocols to achieve a high level of interoperability.